We continue our study of geometry by looking at polygons. Polygons are closed plane figures formed by line segments. By plane figure, we mean it's 2D, it fits on a flat surface. Line segments, we know about those, part of a line with two endpoints. So if you can think about what's the fewest number of line segments that you could use to construct a polygon? If you try it with two, you're stuck, because you can't make a closed figure with just two line segments. So you have to have that third. And so the fewest number of line segments that we can have to make a polygon is 3. And if you think about the maximum number, well, there really isn't any. But consider what would happen if you had 1,000,000 line segments. If they were all made on the same length, the shape that you'd actually be constructing would begin to be looking like this. It would begin to approach like a circle. And of course, there's many kinds of polygons between the 3-sided and the 1,000,000-sided. And we'll take a look at some of the most common. This slide has a chart which shows the number of sides, a picture, and a name of some of the most common polygons. So these are ones that you should memorize. And there's some memory clues to help you. The fact that triangle has 3 sides because tri means 3. That could be helpful. So within the word is a hint. Quad means 4, and a quadrilateral has 4 sides. You might remember that the Pentagon, the building in Washington, D.C., is known because it has 5 sides. It's the shape of a pentagon. Hexagon has 6 sides. Just the X here might help you remember to connect the 6 to something similar in hex. Heptagon, no great clues there. Just remember heptagon has 7 sides. An octagon has 8 sides, like an octopus has 8 arms. There are some others that you're responsible to know, that a 9-sided figure is a nonagon, and a 10-sided figure is a decagon. And you might remember decade has 10 years, just like a decagon has 10 sides. There are names for some of the others when you get higher. Your book has dodecagon is 12 sides, but there's sort of a way that once you get above 10, you can say, if I have an 11-sided figure, I'm going to call that an 11gon. If I have a 12-sided figure, even though it has a formal name of dodecagon, you can call it a 12gon. So a 989-sided figure can be called a 989gon. And one of the attributes of polygons is that the number of angles equals the number of sides. So note that, for instance, in a quadrilateral with 4 sides, we also have 4 angles. And then we're going to look at, in the remaining slides, some other attributes of polygons. The sum of the interior angles of a polygon depends on how many sides and angles it has. It will be different for each one. There's a formula, which is kind of handy-dandy, but formulas while they're useful, it's kind of nice to understand how they came to be, and what can you do to figure out the sum of the interior angles of a polygon if you can't remember the formula. So we'll start with a triangle. It's the basic one. And I'm going to ask you just to remember that the sum of the angles of a triangle is always 180 degrees, because this is what we're going to base a way of figuring out the sum of the interior angles of any polygon. It's going to be based on triangles. So if we have a quadrilateral, well, you kind of know from the previous video that that's 360, and it's because you can make 2 triangles. Draw a diagonal, and a quadrilateral you can make 2 triangles out of, and each of those triangles has a sum of 180 degrees for the interior angles, and the 2 180s make 360. So that's 360. 4 sides, 360. 3 sides, 180. 5 sides. And these don't have to be regular figures, meaning regular figures have every side's the same length and every angle's the same size. But I want to ask, how many triangles can I make out of a pentagon? And the answer is 3. So here's a 180, here's a 180, and here's a 180. So that's 3 times 180. This is 1 times 180, 2 times 180, 3 times 180. And if I have a 6-sided figure, I think I have room to get that in here. The hexagon. I've got 4 triangles. So the sum of the interior angles here would be 4 times 180 degrees. So you can simply construct diagonals and see how many triangles you can make within a given shape. But you may have noticed a pattern that you take the number of sides, 3 sides in a triangle, and you have one 180. With 4 sides, there's 2 180s. With 5 sides, there's 3 180s. So there's a 5-sided figure, 3 180s. 6 sides, there's 4 180s, which leads to the formula that there's always, if you take the number of sides and compare it to the number of triangles you can make, there's always 2 less triangles that can be constructed as compared to the number of sides. So let n equal the number of sides in your polygon. And the formula for the sum of the interior angles would be n minus 2 times 180 degrees. So this is your formula. And all up here is the rationale for the formula. I have sort of an imprecise way to demonstrate the sum of the exterior angles of any polygon. I have a triangle and a hexagon drawn here. The triangle has, I'll just see 3 exterior angles, the pink one, the white one, and the green one. And if you put them all together, if I could separate them and put them all together here, I would get a circle. The hexagon has pink, and these didn't come out very well here, so I was kind of guessing when I put these together. And so just kind of don't go by what the picture looks like exactly, because it's obviously this pink angle and this pink angle are not congruent. And pink was the last one I did, it just didn't come out right. But you get the idea here that if you separate these all and put them together, it would be 360 degrees, just like the triangle was 360 degrees. And so it's to illustrate that the sum of the exterior angles of any polygon, it's always the same number. It's always 360 degrees. So you don't have to have a formula for that. You just have to remember that the sum of the exterior angles of any polygon, if you cut them out and put them together, you'd always make a circle, and a circle has 360 degrees. Regular pentagons have congruent sides and congruent angles. So a triangle would have 3 sides that are all the same length. We call it an equilateral triangle. Each of these sides would be congruent, and each of these angles would be congruent. If we have the same sides and same size angles with a quadrilateral, this has a special name also, as we learned in previous videos. Well, you knew in kindergarten. That's a square. Let's talk about a regular pentagon for a second, and they're kind of hard to draw, so just take a guess at this. I mean, they're not hard to make, but they're hard to just kind of draw freehand. So it probably isn't if you got precise. I know it isn't, but just it means if I'm telling you it's regular and say this represents a regular pentagon, then you kind of have to go with what? This is a regular pentagon, so if that's what you're told, that's what you go by. So with this regular pentagon, we know that each angle has the same length. Each side has the same length, and each angle is the same size. So a typical math problem here would be, what is the measure of the angle in a regular pentagon? Each angle would have the same measure. We know that the interior angles would add up to 3 times 180, because it has 5 sides. So we're going to do 5 minus 2 to get 3. There will be 3 triangles that can be constructed here. There they are. And that would equal 540 degrees. So there's a total of 540 degrees if we measure the exterior angles, and each is the same. So each one would measure whatever 5 divided into 540 turns out to be, and that would be 108. So we know this angle, as every other angle in that regular pentagon, has a measure of 108 degrees. Regular polygons have lines of symmetry, and the number of lines of symmetry in a regular polygon is equal to the number of sides that the polygon has. So I'm showing a square, and the square would have, because there's 4 sides, would have 4 lines of symmetry. I drew in 1, and I wanted to talk about what lines of symmetry are before I construct a few other figures and draw in the lines of symmetry. The line of symmetry is like a fold line or a line of reflection, and everything on one side, so everything to, say, the left of this line of symmetry can mirror image everything over to the right. So I can kind of try to demonstrate that by separating this, turning it over, and showing how I can match directly over top of the one that was to the left. So according to this idea, a triangle, an equilateral triangle, should have, because it has three sides, should have three lines of symmetry, and it would look like this. So I could fold over that way, or this way, or this way. And that's pretty not, you can tell by particularly this fold line, it's probably not a perfect example of an equilateral triangle. It's really hard to just for me to construct other regular figures, so I'll just leave it at that. I'll draw a pentagon perhaps. And just to kind of give you the idea that it should have, and they always get it from the vertex here. They don't always get it from the vertex, but in this case they do. There's 2, 3, 4. There's the 5 lines of symmetry. And they should all cross at the midpoint. So obviously that wasn't a great example, but you get the idea. The big idea here is that the number of lines of symmetry in a regular polygon is equal to the number of sides, and you can draw them in.